Mr. Rainsby here to finish up lesson 9.3, which deals with tests about a population mean. And if you look off to the side, you'll see all the objectives that you've covered. And frankly, you covered all of these really in the last video, which is a lot. Maybe not numerically, but conceptually. And if you haven't figured it out yet, hopefully you will by the end of this video, that when you're performing inference about a mean, that there are a lot of concepts. That's where the bulk of our conceptual understanding has to come from. And whether it's a confidence interval or whether it's a significance test, realize there's a lot to it. And it really comes from our inference flowchart. I mean, if we look at proportions, man, that's just a small little section of it. And frankly, it's either a one sample Z or a one sample Z with matched pairs or a two sample Z, which we'll get to. But when you look at means, notice that is where the more difficult part is probably going to be, because once you realize you have a mean, you have to ask yourself a question. Do you know the population standard deviation? That's the key right here. You need to understand, did it give me the population standard deviation? If so, then you know what? You're going to either do a one sample Z for mu or a one sample Z for difference of mu, which was covered in the last video. And even if you don't, well, it's going to be a one sample T or it's going to be a one sample T for differences if you don't know the standard deviation. But yeah, means are where the bulk of your understanding needs to focus on, because notice that's where the biggest section of your tree diagram is here. And so you need to understand which test am I dealing with. And remember T tests, those have certain criteria. They have those three cases, if n is greater than 30, or if it's between 15 and 30 or less than 30. When can we use t-tests wisely? I mean, there's a lot to it. Remember, if it's less than 30, we have to graph, and we have to prove that we can use a t-test and that it's safe to use a t-test. So be aware, means are where a lot of your understanding has to come and focus on when we're doing inference. And in this case, we're looking at lesson 9.3, which is about means. So now we're just going to dive right in. This slide is the beginning of your notes packet. Please don't flip back, just listen to me. And the first part of this says that, hey, when you're dealing with confidence intervals and significance tests for a population proportion P, you're going to use Z values for the standard normal distribution. What's that say? Well, that's really saying, hey, if I'm looking at proportions, I'm looking at Z's, that part of the flowchart. That's what that's telling you. And so the next part goes in saying, but if you want to do inference about a population mean mu, you know what? We're going to use a t distribution with n-1 degrees of freedom, except, there's a word except, when there are the rare cases that you know the population standard deviation, where that population standard deviation is known. And notice rare cases, because if you know the population standard deviation, there's a very good chance you know the population mean because of the formula. And so be aware, what this is telling you for means, you're going to be using the t distribution a lot of the times because you might not know the population standard deviation. So if it doesn't tell you, you don't know it. Now, in this part, what we're going to do is we're going to focus on what we learned in lesson 8.3 with population means and confidence intervals. And we're going to apply that same understanding to significance tests. And so that's where we're going in this video. And so at the end of Mr. Manico's video, you went over this example dealing with two-sided tests with the Hawaiian Pineapple Company. Now we're going to be using the results of this example to extend into the new concept. So I want to review this example very briefly, very quickly, just to make sure we can get our mind back on the right track. And you were told, and I have a couple things highlighted here for you. In the orange, the last harvest of the pineapples had a mean weight of 31 ounces. And then the purple, a new irrigation system was installed. So hey, here's what happened last year, new irrigation system. So there's a change that went into place. And then we have this green highlighted part saying, hey, the managers wonder whether this change will affect the mean weight of the pineapples harvested in the field this season. And so what they did is they took a random sample of 50 pineapples from this year's. So again, old irrigation system, they grabbed a random sample of 50 after that new irrigation system, and they wonder, will it have an effect? So notice it doesn't say will it improve or will it worsen. It says will it have an effect. It's not specific about direction. It doesn't say is it going to be better or is it going to be worse. So in that case, if it's not specific, if it's just does it impact, then I'm looking at a two-sided test. One thing I do want to address is, so they check for outliers here. Now, do be aware, I mean, your sample size is 50, so that's pretty good. And they do look for the outliers, which is awesome. There are no outliers, as said, but let me also bring this to attention. Not only is your sample size 50, and there are no outliers, one other thing based off of something we learned in 8.3 was look at your mean and look at the median. Those are approximately equal, I would say. They're close to each other. 31.7, 31.9, 35. You would call them really close to each other. And so since the mean and median are close, that's pretty good with the centers as well in the distribution. So it's not just about, hey, is there any outliers or not? It's also about your mean is close to the median. So half the data, when it comes to the median, I mean, hey, the average is pretty close to that half. And that's a good thing when that happens. So be aware of that as well when we're doing this. And then you're like, that's it, I'm ready to go, let's do this. So you did your state and you did your plan, and your null hypothesis was, hey, the mean mu equals 31 because that was last season's, and they did not specify direction, so I'm pretty smart here. I know it's going to be not equal to, it's going to be two-sided, and if I'm going to use mu, I better define mu, and that's what we did. And I need a significance level, so you did your state. Now, do be aware in the plan step. In this case, it said it was random, and you have 50. In fact, that there are no outliers. That makes it okay to use T procedures as well, which is awesome. So again, it didn't tell us in this prompt our population standard deviation, so we're using T procedures. And then we have independence. All right, so you did your plan. Now you look at your do. And so I look at the do and the conclude, which you guys covered as, hey, I have an X bar. I have a standard deviation. Well, wait a minute, Mr. Rainsberg, where did you get those again? That's right, it's from the mini-tab output. It gave us our standard deviation, and it gave us our mean, so I have them. And so that's what we're going to use. And do be aware, standard deviation, not standard error here. So look at that, 2.394. And yep, 2.394 for the standard deviation. Don't accidentally grab this one. I wonder if that would be on a multiple choice and maybe a trick there. Who knows? And so as we go through, that's what you looked at, and then you did your test statistic for T. And you better have stated your degrees of freedom there, which in this case we do. 50 minus 1 is 49. However, table B did not have a 49. And so that means we had to go down to 40 because, well, you can't say you have more of a sample than you really do. And in this case, the upper tail probability is between 0.005 and 0.0025. Now that's new. And that was probably where Ms. Minico spent a lot of time with you, is talking about how in this case, and we're trying to find the area in the tails, we don't know. It's somewhere in between these two. And so that's how he refers to it in the conclusion part. So do be aware that you focus a lot on, hey, our p-value is between this and this. And that's extremely important, is that your t distribution, your t-score is going to tell you the between values. And so you can see what it's between here, but I also have that calculator up above that I can use. And so I can go second distribution, and I'm going to go down to TCDF. Now I don't just want to be able to have the calculator and not know how to use it, thinking that if I have it, I'm safe. I have to know how to type things in. And what happens is, you know what? It's about area to the left. So let me do negative. So I'm going to do negative 100. I'll use the t-scores for this. And, well, what's my upper? Well, if I type in 2.762 with the degrees of freedom of 49, what's going to happen? I mean, hopefully it's between what I said it was going to be between, right? And if I hit enter, oh my goodness, no, it's not. It is 0.995967. Wow, that wasn't even close to what we said it was going to be. So what's going on? Why is this the way it is? Well, because I typed it in wrong. And that's why we always say it's really important that you sketch a picture, because this picture is going to help you even know how to use that calculator up above. And so if I go back to second distribution and I go and say TCDF again, well, if I said it's 2.762, well, if I look at this, that's my lower bound. And so I'm going to do my lower as 2.762. And I'm going to do my upper using the T's. That's where I'll place my 100. Degrees of freedom is 49. And so now if I hit enter, that looks a lot better, doesn't it? 0.004. And so in that case, it is going to be between these two values there. It is between those. And so I feel better about that. So this one's going to give me, if I use the calculator, the exact area. But hold on a second. That's the area on one tail. This is two-tailed. So this I have is 0.0040, and this is between 0.0040. That's right, we have to double it. So even though my calculator's sweet, it gave me, well, I only typed in one section. I better double that p-value because it's a two-sided test, and we always have to double the p-value when it's a two-sided test if we're using our table A. And in this case, you're finding out if we're using TCDF and we're trying to figure it out, then yes, we're going to have to do the same thing here. You're probably sitting here thinking, man, Mr. Isberg, that's a bummer because I bought my calculator and it was $100-something, and that's all it does. I still have to multiply by 2. It doesn't multiply 2 for me. That's ridiculous. And, well, I used TCDF. So, man, I wish there was something else I could have done to check the p-value. And there is. Wow, that's amazing. Our calculators can do such wonderful things, especially with statistics. Because what I'm really doing here is, yeah, I'm looking at CDF overall, the area under the curve, but I'm really doing a t-test, aren't I? So wait a minute, didn't I cover this in a previous video? How do I use my calculator to help me out? Can I go to Stat, Tests, look at option 2, it says t-test? Amazing. I hit enter. Wow, look at that. I already have all the information typed in for us. We had our mean, we had our sample mean, we had our standard deviation of the sample. I have my sample size. I have my fact that it's two-tailed, and I'm going to just go to calculate. And if I hit calculate, hit enter, look at that. It gives us our p-value of 0.0081 if I round. So yes, there is a way to use your calculator to help you with that problem as well that does not involve doubling. But do remember, it is important to realize all the concepts, because maybe you want to use table B. Well, good for you. Then remember, you're going to have to double your p-value. Maybe you want to use your calculator. Well, that means I can use TCDF where I'll still have to double that value. Or maybe I'll use the t-test. But no matter which one you do, overall, you still have to meet the criteria in the state plan do conclude of sketching, labeling, test statistic, p-value, how do they relate to each other. And so be aware of that. All these resources, you need to figure out which one works for you, but understand what you must write down, what you must communicate to get the full credit of the problem. So now we're in the new stuff, but we're still using the information from the previous problem with the pineapples. And so you can see here, I just quickly summarized some of the things. I wrote down our null hypothesis, mu equals 31. Our alternative, mu does not equal 31. I wrote down mu, so I better define it, and I did. And I just wrote down without any context what our conclusion was, which was that we rejected the null hypothesis and we concluded the alternative, which meant, we rejected that the mean weight is 31 and we concluded that it is not equal to 31. But here's what the problem is. I know it's not equal to 31. Does that mean it's better? Or does that mean it's worse? Does that mean the pineapples weigh more than 31? Or does it mean it weighs less than 31? I don't know with the significance test. I just know that it's different. But I don't know if it's good or bad, if it's larger weight or smaller weight. So maybe I should look at, hey, confidence intervals, they get more information. So that's where we're starting. So we have this same Minitab output. A couple things to be aware of, though, as we go through this is take a look at the heading. It says, hey, here, this Minitab output is looking at a test of mu equals 31 versus mu not equals 31. To me, just think about that. That looks like our alternative hypotheses here. And then I have my X bar labeled there. I have my standard deviation labeled there. Well, what else is here? Well, in red, it's boxed in. That's our confidence interval. And what that confidence interval says is that, hey, the 95% confidence interval for the mean weight of the pineapples, all pineapples grown in the field, for this year is 31.255 to 32.616. And what was our main conclusion? We are 95% confident that that interval will capture the true population mean mu of this year's pineapple crop. So what does that mean? Well, now I have plausible values. I have plausible. Plausible. Pay attention to that word. That's the one I want to focus on later is these are plausible values for your population mean. Well, if I look at it, how does this give me more information? Visualize it. So if I visualize it, I can see there's my confidence interval. I can see there's my X bar. Well, where's my 31? Well, 31 would fall outside of that interval. But you know what? It's not just outside. It's not captured by that interval. And I even have to be more specific if I'm going to make this statement. I can't just say it's outside or it's not captured, I better give a direction. Mu is below the interval. So I have my direction. Now, how is this helpful? Well, if I'm looking at this, I have an interval that I'm 95% confident will capture the true population mean. And where is that now? Where is that in relationship to the null of 31? Well, it's to the right. So I have an idea of where it is, where when I'm doing the two-sided test, I don't know if it's less or if it's greater. I just know it's not equal to. But in this case, with the confidence interval, I have the ability to see it looks like it's to the right. And so here's what's really cool about it. I have the ability to get more information on it. So for the pineapples, the two-sided test at the alpha equals 0.05, it rejected the null and it concluded the alternative. But the corresponding 95% confidence interval, it does not include 31. It was not captured 31 in the plausible values. The plausible values of the parameter mu. In other words, the tests in the interval, they lead to the same conclusion about the null. They both led to the same conclusion about the null. The test rejected. The confidence interval did not capture it. Same conclusion. But the confidence interval gave us more information because it gave us a set of plausible values about the population mean. So how are they connected? And so confidence intervals and two-sided tests, the connection between them, the tests and the intervals, are even stronger for means than they are for proportions. And we can prove that because we can look at the two equations as well. If I have here the test statistic for t, and that is the formula for it, what if I want to solve for mu? What if I want to solve for this? Because mu sub O, that's the null hypothesis, isn't it? And so it's really interesting. If I want to solve for this, I would get rid of the denominator by multiplication. And so in that case, I'm going to have t times s sub x over square root of n. And let's see, that would equal x bar minus mu. And well, let's think about this. If I want to do this also, what I'm going to do is I'm going to move the mu over to the left side, and I'm going to move the t star times s of x over square root of n over to the right side, because that way I have a positive mu. And so I have mu equals my x bar minus my t, and I have s of x over square root of n. But do remember, one of them is a test statistic and the other is a confidence interval. And so that confidence interval, we use t star for, don't we? So I have my statistic minus my critical value times the standard error. That looks like the formula for a confidence interval, doesn't it? Ah, you're right. You did notice that. I only have a minus sign. I have x bar minus t star. So where's my mistake on my arithmetic? There is no mistake on my arithmetic. If you knew me, you knew there'd be no mistake on the arithmetic. This plus or minus, it comes from the fact that if we were doing a test, it would be a two-sided test. So you would go to the right, you would add, and you would go to the left, you would subtract. And so this plus or minus is because it's from a two-sided test. So there was no mistake in the arithmetic. Haha. But here we go. So what do we know from this? A two-sided test at a significance level of alpha, let's just say 0.05, and a 100 times 1 minus alpha confidence level. In other words, here's what that means is, let's just say their complements on it is, if your alpha is 0.05, then your confidence level 0.95, 95%. And so that's really what that first sentence is saying, is it's saying they give similar information about the population parameter. I give similar information about the population parameter. If you do not capture in the interval, you reject the null. If you reject the null, you include the alternative. Well, in this case, for confidence levels, you can give me a direction now, because you can see that interval and where it is in relationship to the population parameter. So when the two-sided significance test at level A rejects your null hypothesis, the confidence interval will not contain, because if your confidence interval says we are 95% confident this will capture it, and whoop, there's your mean way over there to the side, and you did not capture it, then it's the same idea as rejecting. It should be in here. Well, it's not. Well, then we're going to reject. And so when the two-sided significance test at level alpha fails to reject the null, the confidence interval will contain it. So if I'm 95% confident this interval will contain the population mean, and it does contain it, well, then I fail to reject the null because the confidence interval did capture it. And so this is kind of just going through with the relationship between them. So maybe make some outline about this. Is if I reject the null, what does that mean for significance tests? And what does that mean for confidence intervals? If I fail to reject the null, what does that mean for significance tests? What does it mean for confidence intervals? And use these red, this green, and this blue box to help you analyze and write down what it is, but also realize it should make sense about it from the confidence interval perspective. If it's between it and you do capture it, well, then you fail to reject because you captured the population parameter, which is what the null says. Now, if it should be between it and it's not, well, then you reject because you did not capture it. And that's what that's telling us over there. And so we're done looking at the relationship between confidence intervals and significance tests, and we're now looking at a new inference method for means. So maybe star this this header, because this is the new stuff we're looking at here, and this one deals with paired data. And so think about that paired data. It's more common to look at paired data because you're looking at comparative studies. How does something old relate to something new? Is there a difference between them? And so in this case, we have a one sample inference is less common for comparative inference. And so this is really dealing with comparing two things with each other. And that's what we call it paired data. Study designs that involve making two observations on the same individual or one observation on two similar individuals. Kind of sounds like matched pairs, doesn't it? Is paired data. So we can make comparisons by analyzing the difference in each pair. And that's what that last sentence is trying to tell us about the study designs that involve. That's kind of talking about matched pairs. We can make a comparison by analyzing the differences. And so when paired data result from measuring the same quantitative variable twice, again, before, after, old, new. And we had that with the job satisfaction study that we did before. These comparisons allow us to analyze these differences for each pair. And if conditions for inference are met, notice the conditions for inference are met, we can use a one sample t procedure to perform inference about the population mean, mu sub d. This actually relates, if you go back to your chapter 7 AP free response that you did in groups, this actually relates to it. So you did an example of this already back in chapter 7. These methods are called paired t procedures. So we have paired t procedures for mu sub d. We have a one sample t for mean differences, mu sub d. We have a paired t-test for population mean, and you have mu sub d. So there's these names we can use. And so now let's kind of go through. If we have a paired t-test as an example, and notice I have it hidden, no peeking. If I'm looking at this and I want to read it, so when we're reading, we got to keep our mind open. We got to start looking for keywords, key phrases, look for values being given to us. And so researchers designed an experiment to study the effects of caffeine withdrawal. And so they recruited 11 volunteers who were diagnosed as being, caffeine dependent to serve as subjects. Each subject they were not allowed to have caffeine, colas, coffee, or any other substances with caffeine in it during the duration of the experiment. And so during a 2-day period, what they did is subjects took capsules that contained their normal caffeine intake. And then during another 2-day period, they took placebo capsules, which means they couldn't tell the difference between the two. Well, then they would know, well, here's the caffeine one, I'll just take that, I'll feel good. Oh, look, here's the placebo. No, look at the next sentence. The order in which the subjects received the caffeine pill versus the placebo pill, that was randomized. So that's good. That means we can do this experiment. We can look at the data from here and draw a conclusion. So at the end of each 2-day period, a test for depression was given to all 11 subjects. And that data you see in the table down below. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. And so that phrase right there, right here, they wanted to know whether it would lead to an increase in depression. So if you think about it, they would want to have, and they would be looking for higher depression levels. They would want to see an increase, which means that the placebo value, if that had a higher rating than the caffeine, well, then when they were withdrawn from the caffeine, they showed more depression. And so they would want to have a larger number. And so pay attention in this table, the order that they subtracted is they wanted to look at is being deprived of caffeine, which was the placebo. That was being deprived because they took the pill and it didn't contain caffeine. If that led to an increase, so in other words, the placebo, they want to know, would that be higher And so I'm telling you this repeatedly because that tells you why they subtracted the way they did. Placebo minus caffeine is they were looking for a higher result. So after the placebo, does that show an increase? And so they did 16 minus 5 to get 11, and so on and so on. Notice down below here in my calculator, I have that table typed in for the future. It's always helpful that if you see I have information typed in my calculator, you should have the information typed in your calculator as well. Because we are going to look at how to use our calculator to help us. And so if I'm looking at this, I'm going to finally remove the black part and surprise, it's state. So if caffeine deprivation has no effect on depression, then we would expect that the person taking the caffeine pill and the person taking the placebo pill would have no mean difference in depression scores. If we suspected that there was no difference, then the numbers should be close with each other. And I mean, look at whoever this is. Caffeine and placebo, 4 and 5. I mean, that to me shows me, hey, there's not much of a difference between those people. But look at 5 and 23. Whoa, that person really likes their caffeine and needs it. They look addicted there. And so be aware. Look at that first sentence as they're telling you what it means. We would expect that if there was no difference, what is no difference mathematically? No difference mathematically is the number 0. And so that's going to be our test. And so we have a one-tailed. I kind of ruined it. We are going to look at it. We want that difference to be greater than 0 because they want to see, they wanted to know, does being deprived of caffeine increase depression? So there's your greater than. It is a one-tailed one. You must state the order that you're doing the subtraction. Notice they did it here in the table. You need to do it as well. So when you're defining your variable, because if you use it, you better define it. And so they're going to say mu sub d equals the mean difference, the true mean difference. And they better say the order they subtracted. Placebo minus caffeine. In the context, depression score. I didn't see a significance level. And so if I don't see a significance level, we use alpha equals 0.05. So there's your state. Things to take away from your state is mu sub d, and the null is going to be equal to 0, that there is no difference. The alternative, well, that's going to be either greater than 0, less than 0, or not equal to 0. One-tailed, two-tailed for not equal to. Is it increasing or is it decreasing? Is it greater or is it lesser? Is it more or is it less? So keep an eye on those same keywords to help you figure out those. And then you define it. In this case, since you're dealing with a paired data and you're looking at the difference, it's mu sub d, the mean of the differences for this one. And you state the order that you subtract. All right, so now moving on to the plan step. Well, you better name the test that you're doing. And so in this case, if conditions are met, we are going to do a paired t-test for mu sub d. So that's a quick way of writing it. But notice we have the name and we have the proportion. We have the name, we have the symbol. And because remember, even in this chapter, you dealt with proportions and you dealt with means. So you always need to state which one you're dealing with. In this case, mu sub d. Random. Well, they were randomly given the order of the placebo versus the caffeine pill. So randomization was met. You cannot say here that the subjects were randomly selected because they were not randomly selected. If we read the prompt up above, it says they recruited 11 volunteers. So I can't say n equals 11 was a random sample. No. What I have to address in this random is, you know what? Hey, the volunteers weren't random. But I did randomize how they got the pill. I randomly selected who would get the placebo versus who would get the caffeine in the order that they got them. So that takes care of the random. So it's not the people in this case, it's the treatment that was randomized. Normal. Well, in this case, our sample size was 11. Which, you know what? Can't do that with the central limit theorem, can I? So T procedures, going through my mind with T procedures, N is not greater than 30. It's not between 15 and 30. Ooh, it's less than 15. I better not have any outliers. I better be able to kind of go through this and see with skewness. And so let's look at that. And well, that's how I'm going to look at it in the calculator. Remember, I'm not going to show you all these graphs in the calculator, but I would go to second stat plot. I would turn on plot 1. I'm going to hit enter. And I have here, I could do a histogram. I could do a box plot with outliers, or I can deal with my normal probability plot. Those are the 3 that they're looking at. And so I would choose one of them, or in this case, I would always do 2 because you want to see outliers and you want to see if there's a symmetric shape. And so if we look at this, we do not know the actual distribution of the difference in depression scores. We don't know it. We don't know if it's normal or not. So that means we better analyze the data that we have. And with such a small sample of n equals 11, you have to look at the graphs. And so they have these graphs already done for us. And we have our histogram, we have our box plot, we have our normal probability plot. Now the histogram has an irregular shape, but there's so few values. The box plot does show some right skewness, but it does not show any outliers. And the normal probability plot looks fairly linear. There, with no outliers or strong skewness, the T procedure should be pretty accurate. And you may be looking here, Mr. Ainsberg, that looks kind of a little bit of skewness, but you also have to realize this is only 11 numbers. And I want you to think about that. You have a min, you have a max, you have a median, you have a first quartile, you have a third quartile. That takes care of 5 of your numbers right away there. So your box plot is going to have a little bit of a different shape. That's why we're saying it's moderately skewed here. It's because the sample size is so small. That's why I do prefer, I like the box plots. The histograms also show you the shape, but the normal probability plot, I can see it's roughly linear there. So it's okay for me to continue forward. And you may be going, I know Mr. Rainsberg has that independent whited out, so I wouldn't copy it down. I got him though, because I know this deals with the 10% condition. All I have to do is take 10 times my sample size and make a statement on how it is smaller than my population, and I'm good. And that is not true in this case, because this case is a little bit different. And so let's kind of see what you should have written down here. So get that eraser ready. And what we should say here is this: we aren't sampling. This was not a sample. This was an experiment. Think about that. This was not a sample. It was an experiment. And so we can't look at it from the same perspective of sampling here. In this case, performing an experiment, this independent one, is different. So maybe make a note here and maybe write something down off to the side of independence rules, sampling versus experiment. Because how you respond in this independent is different, which is why it's really important to read what you're given and what's going on. This was an experiment with the placebo and with the caffeine pill. So we can assume the changes in depression scores for the individual subjects are independent of each other. That means the fact that this person's change will not affect this person's change or this person's change. The change in depression, I like my coffee in the afternoon. If you take coffee away from me, I bet you a person who lives 10 doors down from me here, they might like coffee, but me having caffeine withdrawal is not going to affect him if he decides to do it. Mine is not going to have the same impact. So when you're dealing with experiments, be aware that it is okay, if the experiment is conducted properly here, for us to assume the changes in depression for one person is not going to impact the other, that they are independent of each other. So now let's go forward into the do step. Wait a minute, Mr. Rainsberg's calculator screen changed down below. You might want to pay attention to that to make sure that you go to that same location, but let's continue on. So in the do step, I'm going to state my sample mean, I'm going to state my sample standard deviation. Well, wait a minute, that wasn't given to us. That's right, Mr. Rainsberg did enter the information in his calculator, which means I have the ability to find that by going stat, calc, one variable stats, and I want to use L1. I'm going to make sure nothing's in my frequency list, and I'm going to hit enter. There we go. That's where I get my information. But I do want to pay attention. Notice what my standard deviation is here, 6.918. Notice what's right below that in the calculator, 6.5957. That is if it's a population. This is a sample. And I'm telling you this as little red flags, little hints, as maybe one of those would be a choice on the multiple choice portion of the test. Like, you have to be aware of which one to grab. And so this is a sample, so I'm going to look at 6.918. So plugging in is very simple to do. I have my mean there, which is 7.364, minus my null. Well, that was 0. There was no difference. So in this case, that's where I get my 0 from here. My H sub O said that my mean, my mu sub D was 0. So that's where I'm going to get that. 6.918 divided by the square root of 11. It gives me a T score of, a T statistic of 3.53. My brain's going off. That's on the right hand side. It's above 3 standard deviations from the center. Wow, that's pretty far in the tail, right? And if you were to think about that, that's going to have a small p-value here. Now, I'm going to use technology. And you could use your table to help you out, but I'm going to use technology. I'm going to go to stat. I'm going to go over to tests. Well, which one do I use? Am I dealing well, I'm not dealing with a 2-sample z-test. Am I dealing with a 2-sample t-test? Is that what this one is? A 2-sample t? But no. And you might be tempted to choose that, but you have to realize and go back to this, you know, how many, if we looked at our sample, we only had 11 people. It was one group. We performed 2 things on there. We did a matched pairs for it. It wasn't that we had 2 samples. It was 1 sample of 11 people that we did something on. So this is not, and you know, maybe you want to make a note here, that it is not a 2-sample t-test. We'll get there in the next chapter. Right now, you're still going to use a t-test that you did before. However, I'm going to use the data, something new. Let's see, my mu, if I use my data, was 0. My list is L1. And if I think about this, we wanted what? We said greater, correct? When we're looking at this, I'm going to go over to greater. It did say according to this, and we're going to, well, you know what? I'm going to draw this time. And let's hope I don't have anything in there from pre-calculus. So, ooh, dimensional error. That's not, oh man, that's embarrassing, isn't it? I mean, I have a calculator problem. I mean, what did I do wrong? That shouldn't happen, right? I mean, t-test, right? Mu, L1, boom. I mean, this looks good. I'm going to do it again. Error. Why do I have an error? Because that's going to happen to you as well. Well, maybe I have an error because I turned on something. And so knowing how to use your calculator is extremely helpful. So look at that. I'm going to turn off my plot 1 because what it's trying to do right now is it's trying to graph my plot 1 that I'm looking at, and it's also saying, hey, at the same time, look at this little test over here is 2 conflicting things because plot 1's turned on and it's trying to graph this t-test. It doesn't work that way. So I cannot have any of my plots turned on when I'm trying to do this. So let's see. Let's see if that works. I'm going to go t-test. All my information was right because you know what? It's me. I did enter my information in. So we know it's good. And I'm going to go down, boom, 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 boom. And I'm going to go to draw again. And let's see if I am right. That I cannot have my plot 1, plot 2, or plot 3 turned on in order to do the test. Look at that. No error. Awesome. So here's what we have. We have the picture. And notice you can't really see the shaded region there. Well, our degrees of freedom is 10. We get a 0.0027, you see. So that 0.0027 is way less than our alpha level 0.05. So that means we can reject the null that mu sub d equals 0. And therefore, we can conclude that there is enough evidence for the alternative. That depriving these caffeine-dependent subjects of caffeine did cause an average increase in their depression scores. That is the context of your conclusion. We rejected the null, that there is no difference. That is what that first part is saying, is we have enough evidence to reject the null, and we can conclude the alternative. That the people who are caffeine dependent, if we took caffeine away from them, it did cause an average increase of their depression scores. Primarily what I want you to see is how to use the technology and how when you're going to have errors appear. So pay attention to what you do in your calculator and how it affects things. And you may go, Mr. Rainswork, I'm intimidated by the calculators because look at that had an error, and if I was taking the test and I had no idea what's going on, I would freak out. So I like to use table B, and good for you. Keep to the old stuff like slide rules, let's say. And so when you're looking at this, it's not a bad thing, is 3.53, I have to kind of be aware my degrees of freedom here is 10, so I go down there, 3.53, well that looks like it's between. And so how you respond to this one is you would say the p-value is between. So I'd say my p-value is between lesser, so 0.0025 and 0.005. And really ours was, remember, our p-value was 0.0027, and so it is between there. So if you're going to use table B, you need to state that it's between certain areas. So be aware of that. It's nothing against it, but you do have that to work with table B as well. So moving on to using tests wisely, you can go through these comparative tests. They are used or even just general tests on. They want to know, does a certain advertisement work better than another one? Is there a change in it? So carrying out a significance test is simple, especially if you have a calculator or technology that you can input the information in. But you need to make sure using tests wisely. That's not the easy part. Some points to keep in mind you can see down below. Statistical significance and practical importance is when a null hypothesis have no effect or no difference for a comparative, if it can be rejected at the 0.05 or even the 0.01 significance level, there's good evidence of a difference. But that difference may be very small. And so you actually have to look at that stuff. So remember, significance tests, you also have confidence intervals you can take a look at as well. Do also be aware, when large samples are available, even tiny deviations from the null hypothesis can be significant. So when you have null hypothesis, when you have a large sample there, even tiny deviations can be significant. Some other things to keep in mind. Do not ignore lack of significance. There's a tendency to infer that there is no difference whether a p-value fails to attain the usual 5% standard. In some areas of research, small differences that are detectable only with large sample sizes can be of great practical significance. Now that sounds pretty similar, right? Small differences that can only be detected with large sample sizes can have great practical significance. That sounds like the same idea here. So when planning a study, verify that the test you plan to use has a high probability power of detecting that difference of the size you hope to find. Statistical inference is not valid for all sets of data. Badly designed surveys, badly designed experiments can produce invalid results. You can finish reading the rest of that blue one. And be aware of multiple analyses. Statistical significance ought to mean that you found a difference in what you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking. You design a study to search for it and use a significance test to weigh the evidence you get. In other settings, it may have little meaning. And so really just be aware, here is kind of what we're going through. When a null hypothesis can be rejected at the usual levels, 0.05 or 0.01, we can say there's good evidence of a difference. In even larger sample sizes, tiny deviations are something to be aware of. So we have large sample sizes, even tiny deviations from the null hypothesis are considered to be significant. The way you interpret your finding is dependent on the effect of the size and sensitivity of the test. Outliers can destroy the significance or other convincing evidence, and kind of be aware of that. If you have an outlier, it's going to pull the mean away from where it should be. And so that's what that's telling you. Remember, if you have outliers, that's usually not a good thing to look at. The mean is because the mean is impacted by the outliers. That's what that was trying to tell you, is if you have outliers, it could destroy the significance of it. Number 4, significance tests just ask if the difference is too large to have occurred by chance, while a confidence interval estimates the size of that difference. And so keep that in mind. Remember, confidence intervals provide us with more information. Significance tests just tells us, is there a difference? And when planning a study, verify that the test you plan to use has a high probability or high power of actually detecting a difference of the size you are hoping to find. And so that's really the using tests wisely part of the lesson. Thank you for watching our video. Please remember to both like and subscribe so you can get future updates when we make new ones. And remember to support our advertisers who make videos like this possible. Today's video was presented to you by Slide Rule. That's right, Slide Rule. Ever forget your calculator at home? Ever have the battery die in the middle of the test? Have no fear, Slide Rule is here. That's right, performing calculations is as easy as a slide. Need to find sine of an angle? Slide Rule. Need to find the log of a number? Slide Rule. You can use Slide Rule for all of your calculations in your math classes. And if you act now, they will throw in this wonderful carrying case to keep it safe. Just slide it in, and it'll fit in your pocket. Psst, psst. What? What do you mean no one uses slide rules anymore? Looks like we lost our advertisers, but hey, still like and subscribe.